Okay, thanks again to the organizers for inviting me. It's certainly much more pleasant to spend a couple of weeks in sunny California than back in South Bend dealing with several feet of snow. So this talk is on spatial coupling. I think it looks like it's maybe the only talk in the workshop that's completely on spatial coupling. I mean, Tom and Andrea both discussed kind of briefly a higher level view of spatial coupling from the point of view of exit charts and g-exit charts. And I think there's a talk on Friday. Florent, I think, has something on spatial coupling in your talk, but this talk is pretty much completely on spatial coupling. These are the guys that do all the work, and I'm the one that gets to come to California and give the talk. And you know, some of you know all those people. So I'm just going to give a brief run through of LDPC block codes from the point of view of background, spatially coupled LDPC codes. Again, a little on the brief side, and we'll concentrate more here on these considerations. This is compared to what Tom and Andrea talked about. This could be considered more of a nuts and bolts type of talk. Okay, and primarily in the third part here. And I titled it a comparison, okay, and I left the word fair out. See if it's fair or not. So most of you know this picture. Okay, we've got an H matrix, describes an LDPC code, although you can't really get an LDPC code on a small screen like this, but can't put too many ones in it, but it's described by a graph, and of course this is a JK regular code, it has a certain rate associated with it. And of course, we can use low complexity belief propagation iterative decoding for codes of this type. Now, one of the things that's interesting with regard to ensembles of codes is the minimum distance properties. So regular LDPC block codes they have the property that they're asymptotically good ensembles in the sense that the minimum distance grows linearly with block length. So in particular, that means that there's a typical minimum distance ratio or a minimum distance growth rate, which depends on the degree profile of the regular code, the J and K, with which the minimum distance grows linearly with n. And of course, there's a penalty to be paid in terms of distance for the low density, the easy encoding, and you can see compared to the Gilbert-Varshamov bound, here's the penalty that gets paid. And the sparser the code is, the more the penalty you pay in distance, and the more dense codes get closer and closer to optimum codes in terms of distance. Okay, and I guess I said that. So now thresholds of JK regular LDPC block code ensembles. So here's a little table of BEC thresholds. I'm just going to comment on the rate 1/2 ones on top here, and corresponding Gaussian thresholds. And a couple of things to notice with JK regular ensembles is that there's a significant gap to capacity, whether you look at the BEC or the additive white Gaussian noise channel, and also that as you increase the density, which you'd like to do in principle if you want to get more distance, say, for example, you're going to get worse compared to capacity in both cases. So that's just something that we have to deal with JK regular block codes. Now, I'm going to just briefly talk about protograph representations because most of the work we've done and the way I'll explain spatially coupled codes is from the point of view of protographs. So a protograph is representation is a compact representation. We can start, if we like, with a so-called base matrix, just a small parity check matrix of a block code. And it has an associated Tanner graph associated with it. Since it's a small base matrix, it's a small graph. We call it a protograph. And of course, this goes back to Thorpe about 10 years back. And then we can use a lifting process to generate a large H matrix by replacing non-zero elements in the base matrix with permutation matrices here in the larger matrix. And if you can have integers greater than 1 here, it's just the multi-edge type construction in which you get sums of permutation matrices up here. And you get the multiple edges down here in the corresponding Tanner graph. So every member of a protograph-based ensemble, though, does, when you use this lifting procedure, preserves the structure of the base protograph. So you can apply density evolution to the protograph to find out the thresholds, the iterative decoding thresholds, which is nice. So you can create ensembles like this, and you know their thresholds by computing them on the protograph. And also from the protograph, you can determine average ensemble weighted numerators, which allows you to determine the distance properties, in particular if you happen to have an asymptotically good ensemble. Now, one of the I didn't mention irregular codes here, but irregular the spatially coupled codes, in some sense, they can be viewed as trying to combine the best properties of regular codes and irregular codes. The regular codes, as we saw, you can get, they're asymptotically good in terms of distance. The irregular codes, of course, can do much better in terms of thresholds. So the spatially coupled codes, we can consider it this way. Here's a base matrix with the corresponding protograph. This is of a multi-edge type. It's just one way of representing a 3/6 regular block code. And we can consider transmission of code words successively from code words drawn from this ensemble. Now, we can change things by spatially coupling, just introducing memory between consecutive protographs here. And one way of talking about this is we can so-called spread the edges over time. Otherwise, we can take this graph and spread these 3 edges over, say, the next 2 time units, or the next 2 parity check symbols in this graph. And that's equivalent to taking this base matrix B and splitting it up into 3, in this example, 3 individual submatrices, B0, B1, and B2, all of the same size. And there's a so-called memory associated with this edge spreading of 2, which means we've taken edges from here and jumped over 2 protographs, or connected over to 2 protographs. So there's different edge spreadings that can be used, and sometimes they can result, even for the same base matrix, they can result in different properties, different asymptotic distance properties, different threshold properties. Oops. Okay. Graphically then, if you put the whole thing together, a spatially coupled Tanner graph results in what we could also call a convolutional protograph, because the coupling, the introduction of memory between these successive block protographs really makes the block code into a convolutional code, and we get a so-called convolutional protograph. And that has a so-called bi-infinite, in this case, since we're not talking about any kind of termination yet, convolutional base matrix, which has the familiar diagonal form of the parity check matrix of a convolutional code. And it has a rate associated with it. These parameters go back to the parameters of the base matrix that we started with, that we coupled. And as a convolutional code, it has a constraint length associated with it, which is basically just the number of symbols. The other parts of the base matrix here are all 0. So the number of symbols, the number of columns in the non-zero portion of this diagonal would be the constraint length. And of course, this is still a base matrix, and this just gets lifted in the same way that the base matrix of block codes gets lifted. These are the sub matrices when we did the edge spreading, and wherever we have ones or non-zero symbols, we put in large permutation matrices to create an ensemble, a spatially coupled ensemble. Now, of course, terminating spatially coupled codes, we always have some starting point, and then we can also terminate at the end by just doing this, just chopping it off at the end of one particular column. And there's a rate loss associated with termination, where L is kind of the termination length. But for large L, if you terminate after so this is a large number of protograph sections, the terminated code rate approaches the original design rate of the original protograph, if you want. Okay, so for example, if we take this 3/6 example with this base matrix, that we have a memory of 2, so we spread the edges over 2 adjacent sections, a very small L here of 4, otherwise I couldn't get it on one page. The rate here, this is the design rate is 1/2. This is all the way down to 1/4 for the short L. But this is what the convolutional base matrix would look like, and this is what the corresponding Tanner graph would look like. And the key thing to notice here is that even though this is based on a regular block code and maintains to a large extent, especially for large L, that same regular structure, the check nodes at the ends have lower degrees. Otherwise, the check nodes in the middle all have degree 6, but the 2 at this end, one of them has degree 4, one of them has degree 2, and same at this end. So these are stronger local constraints at the ends of the convolutional protograph, which is crucial in allowing us, in giving us the improved thresholds of these types of constructions. So these can be, I think I said this, but lifting can be used. You can vary the lifting factor and the termination length to get ensembles of different lengths and rates. Okay, and so there's a so-called wave-like encoding. As I mentioned, the variable nodes here are all going to have the same degree as the underlying block codes. The check nodes also the same degree, except at the ends. And that's what improves the belief propagation decoder. So here's a little picture. This is BEC channels. This is just time. These are numbers of iterations as we go to the right here. And this is kind of after 10 iterations. And you can see the error rate in the beginning, or in the middle here, is 50%. But things have improved a little bit at the ends here after 10 iterations because of these strong local codes at the end coming from the low degree checks. And as we do more iterations, 20, 50, 100, so we see the improved performance propagating towards the middle from both ends, which is the so-called wave-like decoding associated with spatially coupled codes. So eventually, everything gets good. So and the thing that is important to realize too, the fraction of these lower degree nodes at the ends, which gives us this nice feature, really goes to 0 as L goes to infinity. So we sometimes refer to these as asymptotically regular codes or almost regular codes. So the idea is we're trying to preserve the regular structure so we get distance, and yet also get the threshold performance of more often associated with irregular codes. So we can do density evolution, as I said, on the protograph to determine thresholds. And this is an example for BEC. So here is the Shannon limit for rate 1/2 on the BEC, which is 1/2. This is the Shannon limit for the other rates associated. Remember, as we vary L, we change the rate changes. It starts out at a low rate. So at the low rates, like L = 4, the Shannon limit is 0.75. And our spatially coupled limit has a gap there. It's only 0.635. And for L = 10, and our rate is up to our rate is up to 0.4. The Shannon limit's at 0.6. And we're a little closer to the Shannon limit in that case. And this continues to the point where these are the spatially coupled thresholds, which come to 0.488, very close to the Shannon limit. Those of you that know this know that this is the map threshold, actually, even though we're still doing, we're still basing this on belief propagation. Whereas the 3.6 regular block code that we started with has this 0.43 threshold associated with it. So we get this step up in threshold very close to the Shannon limit and actually at the map threshold. So looking back at a table like this, so iterative decoding thresholds for spatially coupled codes, so we have significant improvements relative to the corresponding block code thresholds, the block code thresholds of the corresponding regular codes, erasure channel, Gaussian channel. And what's really different here and noticeable is that as the density increases here, the thresholds increase rather than get worse, as they did in the block code case, which gives us improving thresholds and improving distance properties as we increase the density. So another way of looking at this is that, this is again BEC. Once you know symbols perfectly, you can kind of remove them, and the graph kind of collapses to the middle. So this threshold saturation was observed. There was numerical work in this paper showing that they're indistinguishable from map thresholds as L goes to infinity, and then proofs were given analytically in a couple of more recent papers, both for the BEC and then more recently for more general channels, that the so-called threshold saturation effect. So another way of viewing this is, let me start here. So this is block codes, and we see here, this is again erasure channel, map threshold, BP threshold, simulated performance. I can't remember the block length, but it was pretty big. And you see as we go from 3.6 to 5.10, the block code performance follows the BP threshold. Okay, and gets worse because the BP thresholds are worse. The map thresholds get better, okay, with increasing density. And since the spatially coupled codes follow, even though we're using belief propagation decoding, they follow the map thresholds. So the 3.6 is here, close to the map threshold. The 5.10 is even better. It moves with the map thresholds.
How big do you have to have it so that you actually get close to this?
Well, big. I mean, I'm trying to remember what 100K maybe. I don't know. What would you say, Rudy? To get really
30, 40,000. I mean,
yeah.
You need the length per section. Okay, you need that to be. There's a finite length gap associated to that, which is the scaling one of the script.
Rate law. Yeah, the rate law.
Beat that. Okay, and then you need the rate loss to be reasonably small, and that's unique.
I think these might have been, I don't remember, 60,000 or something like that.
It's not that big.
So BEC, now, so here we just plotting, so these are the thresholds. Now again, there's a curve of thresholds associated with each. This would be the 3.6 curve because the short termination lengths have very low rates, and then the thresholds are not so close to the Shannon limit until they get up, until L gets very large. Okay, and we can see with the 5.10, you can see that it actually gets there. And these are distance results. This is again, the spatially coupled codes have a range of rates associated with them, depending on the termination. And they're asymptotically good. Now these are the minimum distance properties of the underlying block codes. So these are the minimum distances of the associated spatially coupled codes depending on the rate. They stay asymptotically good. The distance, though, goes towards 0 as the termination length gets large. And similar results can be obtained for the Gaussian channel. Obviously, this is the same curve because it's the distance curve. One point I want to make, though, is I don't, with spatially coupled codes, I don't think minimum distance is the right way to measure the strength of these codes in terms of, like error floor performance. Well, obviously, there's trapping sets and absorbing sets and things of this nature, but just in terms of distance, because I think it's clear if you think about it, the performance of these codes is not going to get worse just by increasing the termination length. Okay. And these are convolutional type codes, so it's more the free distance of the underlying unterminated convolutional code that I think is, we don't have any firm results on this, but we do have bounds on the free distance, and the free distance to constraint length ratio does not depend on L and stays constant. And it's reasonable to say that an appropriate distance measure for these convolutional-like ensembles should be independent of L. Okay, unlike the minimum distance ones, which are getting worse as L gets larger. So this is something we want to investigate further. So some practical considerations. So spatially coupled code, again, you can look at just the decoding as coming from both ends like this, towards the middle like we showed with that wave-like picture. But the highly localized, the convolutional structure makes it easy to do using decoding schedules that reduce memory and particularly both memory and latency requirements. So a sliding window, which actually Lentmeyer used to actually do the density evolution analysis of these codes, and then Paul's student Arvind actually was the first to propose using sliding window actually for decoding. Okay, so the sliding window decoder works like this, and if we compare performance, so this is this is for a block code with a lifting factor of 1,000. These are all 3/6s. This is a convolutional code, spatially coupled code, lifting factor of 1,000. I always had to bite my tongue whether I'm going to say convolutional or spatially coupled. With different lifting factors and different window sizes. So with the same lifting factor, we get quite a gain with the spatially coupled code. It's not really fair because if you compare the latencies, because of the window size, the spatially coupled code is going to have a larger latency. But if you do it on an equal latency basis, so you would make the window size then, or the lifting factor smaller, depending on the window size you're using, so that the latencies are the same, you still get a gain, a couple tenths of a dB. And you can play with the lifting factor and the window size to try to get as much gain as you can for the spatially coupled code. This is kind of flexibility that's not built into the block code. Now, I won't say anything much about finite length scaling. This is just some results from Pablo and Rudy's paper, just showing that the analysis does match simulations very well. I think Rudy talked about this comparison the other day in his brief presentation, but just the comparison of the scaling behavior of spatially coupled codes compared to polar codes is better with regard to LDPC codes, which would just be block codes here. Not as good, but the comparison is uncertain because the block code comparison is with threshold, and here we're comparing with, or the results there compared with capacity. Okay, what about, this goes back to equal latency again, and this picture shows the required signal-to-noise ratio. This is Gaussian channel simulations needed to get a certain latency. And you can see that, so the block code curve is the black curve. And these are the lifting factors associated. These spatially coupled curves are different colors. And they all have different lifting factors and different window sizes. Again, there's this trade-off. And we kind of see so the blue is the smallest lifting factor, and then the other curves, the lifting factor and window size are adjusted so that the latency is whatever it says here on the x-axis. And we kind of see again that we have several tenths of a dB advantage with the spatially coupled codes, as long as we're talking latency larger than something. Okay, in each case, the block code will win at smaller latencies, but at larger latencies, the spatially coupled codes will perform better. And just in general, in looking at these parameters, this trade-off between lifting factor and window size, the large lifting factor will improve code performance. The large window size will improve the decoder performance. Now, these are complexity trade-offs. Now, it's just node updates. We just counted node updates. And these are for different latencies or different lifting factors. And basically, you can see here, this includes non-binary. So this is a block code curve here. And let's just take one for comparison. This is the spatially coupled code curve here. So you can see the spatially coupled code does pay some penalty in complexity, which grows with field size. I mean, here's the comparison down here for binary. Okay, this is for equal latency. But the spatially coupled codes, of course, have a performance gain. And one thing to point out, and this is with stopping rules. Both codes were decoded with stopping rules. One thing to point out is you could give the block code more iterations, say, but it's never going to make up the performance gap. Okay, so the performance gap is there. It takes a little more computation to get it with this spatially coupled code, but for this latency, the block code will not be able to get there. This is a funny graph. So we're fixing performance, 10 to the minus 5 bit error rate at 1.5 dB. And we're plotting latency versus computational complexity. So how do I want to try to show this? Okay, let's take binary. This is the block code, and this is the spatially coupled code. So same performance now. So the spatially coupled code gets the same performance with more than a factor of 2 less in latency, a little bit more computation. Same thing more or less with 4-array. A big improvement in latency, more than a factor of 3 here. These are based on random codes, and you could argue about how, you know, if you did this or that or something, but they're representative, I think. Again, a big improvement in latency, but just for a cost of only a small increase in complexity. Good trade-off. Here we go to 8-array. It's the same type of picture, block and spatially coupled, but notice to get a little less latency, you're paying a lot in complexity in both cases. And in fact, here, with the block, you're going backwards. You're worse in complexity and in latency. So it seems like GF4 may be a sweet spot where you get a good balance between complexity and latency, and for the same performance, you get an improvement. Now, we did I'm running out of time. We did a comparison with irregular codes. Okay, because that's the other thing. Well, you're always comparing with regular. What about well-designed irregulars? The basic thing is we took an irregular which had roughly the same rate and the same threshold as our spatially coupled code. And what do we expect? Well, the spatially coupled code is based on a regular structure, which the irregular code doesn't have. So the spatially coupled code somehow should do better in terms of error floors. We expect, or we hope. And this is at least the preliminary simulations we've done. This is the spatially coupled code, and this is the irregular code. And we allowed a maximum of 100 iterations here and only 10 here. Because we have a window of 8, so the computation complexity is roughly equivalent here, because we have a shifting window. So those comparisons look reasonable. They also look good compared to irregular codes. Haven't done a lot of these. This has to do with random puncturing. And then, of course, these last couple of slides just say that you can also spatially couple irregular codes. These are ARJA codes, very good irregular codes that are asymptotically good, and you can spatially couple those also. So hardware advantages, would there be advantages with quasi-cyclic designs? We have this asymptotically regular structure. We have a flexible frame length feature by varying L and flexible rate feature by puncturing. And of course, there's ongoing work in looking at stopping sets, trapping sets, and absorbing sets with regard to error floor questions. So the spatially coupled ensembles achieve threshold saturation. Thresholds approach the map thresholds of the underlying block code ensembles. They combine, I think this is the key thing maybe, the best features of JK regular and irregular block codes are kind of combined with spatially coupled codes. And with window decoding, they compare well with block codes in the finite length regime in terms of equal latency and complexity type of comparisons. So thank you. I'm sorry I took a couple extra minutes.